Okay, so hello everyone, I'm Chaoqi Liu.
I'm Jia Huili.
Well, and this is a video presentation for the CS128 Honor Session 2022 for final project, and our team name is Nano Rescue Squad.
And this is our intro to Huffman coding. It was invented by David Huffman in 1951, and the Huffman coding algorithm is a fundamental data compression algorithm. It is used to compress files, communication network, and computer security. And this is one simple example of our Huffman tree visualization.
And the next part will be the technical overview. Like for this project, the data structure we use a Huffman tree, of course. Like the left path represented by 0 and the right path represented by 1. And the numbers in each node represent the character's frequency. The numbers here. And the number on each edge represents the direction to take on the tree. For instance, to encode characters S, the value would be 100. And this is how we build a Huffman tree. The functions here, and we follow the step on this page how we build a Huffman tree. First, for example, the input is feed me more food. Step 1, we would calculate the frequency of each character in the text and order them by increasing frequency and store them in a queue. And we name this queue to be single queue here. Step 2, we will build the tree from the bottom up first by taking two least frequent characters and merging them together. For example, for this one, we will take R and D to build a subtree called RD and push it into a merged queue. This one, merged queue. And the code always also shows this by like we got a left node by remove the smallest one, and the right node remove the second smallest one, and create a new node called current, and set the current left to be left and right to be right, and push the current into the merge queue, and we run the loop. And for step 3, we repeat the step 2 and also considering the elements in the new queue, the merge queue. For example, this time we will pull out F and M and create a new subtree called FM, and we keep going until we got only one node in the queue, which would be the root. Yeah, the root. Okay, yeah, this one. This can be shown here as well. This while loop only ends when there's only one node in both queue. After that, we would mark the left node to be the root node.
And this is the part for input and output. As you can see here, here's our functions to read from text file, read from binary file, and write to text file, write to binary file. And this is a coding trick we come up with. Since the binary file store information in bytes, however, we cannot always get number of bits as multiple of 8. Therefore, bits that are insufficient to form the bytes will be lost. This is why we need to add complementary zeros in the front. Firstly, we need to determine the number of zeros we need to add on, and here's 3. And besides, we're gonna add one extra bytes at the very beginning, which represents the number of complementary zeros. So as you can see here means 3.
Okay, so next part is optimization. Like we implement the MapReduce algorithm to improve the efficiency. Like as mentioned, at the very beginning, we need to count the frequency of every characters and to build a tree, and this process is very is time consuming. Thus we have to come up with a new algorithm, which is the multi-threaded mapper to improve the efficiency of building a Huffman tree, and this is how we implement it. Besides this, we also have built a robust exception handling system. For example, for the input and output part, every function will return a result enum, which will panic if we have typo in the command line or others happen.
Here I'm gonna go through the steps on how to run our project. First, we need to clone the repo to our local. And then go to Huffman directory. And we can run cargo run help to see what
operations we have. Yeah.
and I'm gonna create a input file, and we can edit it. This is a test for half-man tree, and I'm gonna use this to encode it. It says successfully write to output file. So and we can print the half-man tree by using this code, print half. It is shown above, and we can use this code to decode the file. We name it as decoded. And we can use this code to see if there is any difference between them. So it says nothing, it means those two files are the same. Also, we can check from here.
Yes, that's
yeah.
the same.
And we can run, and we have an simple image ppm, so we can run cargo run compress sample image to compressed. It takes a few seconds. And we can depress it to depressed. To depressed. And we can also use diff to see if there is any difference. And sample image dot ppm, and it says not.
Yeah, time.
Oh, sorry, I got a typo. Oh, and it says nothing. It means those two ppm are the same.
Yeah, it's the same.
As we can tell from here also. And by using this code, we can see the size of the file. It's compressed. Yeah, the size of the original file is this, it's this, and the depressed size of the file is for and the compressed size is this, so it drops significantly from for almost a half.
Okay, and that's all for the presentation, and I hope you guys love the tool we provide. Yeah.